This video is for 16.3's lesson. So if you have not already done the Spark, then go ahead and try that out and think about if you can figure out what Jillian needs on her test, and then come back and see how I thought about this problem. So this tells me that Jillian has taken 5 tests and they were each worth 100 points. Her scores here are shown below. What score does she need on her next test to have an average of 90? So I know she's going to take one more test, and she wants these, when I add them up, to be my total divided by 6 equals 90, or she'd be happy with something higher than that, but she wants at least 90. So it's greater than or equal to 90. So here we know this is what she has so far. So we're going to start with how many points does she have so far? So she's got 88, 85, 89, 92, and 90 points on her test so far. So we're going to add those up and see what she's at. So here is 13 plus 2 is 15. 9 more is 24. 8, 16, 24, 25, 26. 9 more is 35. 9 more is 44. So far she has 444 points. Now I need to figure out, what does she need? What is this total going to be? That's right. I know she wants an average of 90. So I would add up all 6 of these scores for her next test once I knew that. And I would divide it by 6, and she would want her average to be 90. So we're going to work backwards and find this t by itself. So the opposite of divide by 6 is to multiply by 6 on both sides. So we're looking, this cancels out. So that's 1. And then 90 divided by or times 6 is 540. So she needs a total of 540 points. She has 440 so far, and she gets to take one more test. So we're going to subtract and see how many more points does she need in order to get at least 90. So we're going to borrow here. Here's 6. Borrow here is 13 minus 4 is 9. So she needs at least, so T needs to be greater than or equal to 96. So she could get 96 points and get an average of 90. She could get 97 points, 98, 99, or even 100, and that would bump her up to 90 as an average or higher. So because she had a couple of these scores in the 80s, she's got to bump a score up into the 90s to kind of meet in the middle there and fair share her scores to the 90s. So she needs an average, or she needs her last test to be 96 or higher. So today we're going to kind of think about, how is that data spread out and what is that telling us, right? So we know she had to get a little bit of a higher test score to pull everything else up. So we can see how that was her data was distributed. Sorry, how it was spread out. So we are going to be working on finding the mean absolute deviation, and you can also call it the MAD, mean absolute deviation, the MAD. You might see it abbreviated like this, and it might make you a little mad when you're doing it. But here's the thing. It is not hard. It's just another step, but it's a step you guys can do. It involves subtracting and finding the average. 2 things you can do. So let's get in the right mindset and tell ourselves that we can do this. So the mean absolute deviation is our goal today. Find it. If you can find the mean and you can find the distances, that's a 2. And if you can take it the step farther, that's a 3. So if you can find the mean, I know you can do this. If you can find the mean, that's a 1. So I think we're all here. I even think we can all do this. So I'm pretty sure we can all do this. So if you can find the mean absolute deviation, it's not a straight line, and tell me what that means about the data. Was it spread out? Is it packed together? How was it distributed? Then that is the fourth. So we're looking to find the mean absolute deviation. So let's jump in and see what that actually means. So Helen and Jeff record the time in minutes they spent practicing the piano this week. I'm just going to pull that down over my words a little bit. So how long did they practice the piano? Every day. There's their minutes. So the first thing we want to do is find our means. So we are going to add these up and divide by 5, add these up, divide by 5. So I can see here is 60 and 90. 20 more is 110. So I'm going to come back and grab that 5. 30 more is 140, and 10 more is 150 for Helen. And I'm dividing that by 5. So go ahead and do that. So I can see her average is 30 minutes per day. So if she fair shared all of her minutes, she would have done 30 minutes every day. Some days she did more, some days she did less than that. Now, Jeff here, I can see 5 and 55 is 60, and 30 makes 90. 10 more is 100, and 40 more is 140. 5 and 5, 150. So if mental math is not your thing, and guess what? It's not mine. I've had to practice at it, and I still look for those compatible numbers. So if that's not something you are interested in, list them out, add them up. Okay. I don't care how you get your answer, just get your answer. So Jeff also practiced 5 days. We can see here 150 divided by 5 is 30. So overall, this tells me that Helen and Jeff both have an average of 30. Let me shrink that up so we can see it a little better. So Helen and Jeff both practiced the same amount of minutes. They both did 150. They just did it at a different rate or a different pace. So he started off really strong and then kind of did less throughout the week. And she kind of had to do a little bit more because she didn't do as much at the beginning. So I noticed, right, they're the same, but that doesn't mean they did it in the same way. Their data is not the same. So it would be hard for me to really compare them because I can't really describe how it's distributed or how it's given out because my mean is saying that they're the same. So what we're going to do is we're going to take it a step farther and we're going to see how do they distribute the data. So we've got the mean average or mean absolute deviation. So we know the mean is that average here. So we're finding the average, adding them together, dividing by how many there are. Absolute is another vocabulary word we've had this year. So the absolute value is just telling us how far this number is from 0. So if I have 7, that means it's 7 units away from 0. If I have -3, that's -3, or sorry, that's just 3 units away from 0. So it's always a positive amount. How far is it from 0? And then this word deviation here, when you deviate things, you're kind of changing them. So how does it deviate? If you deviate from the plan, right, you're kind of changing the plan. So instead of all the data just being 30, we're asking how did they separate themselves away from 30? How are they spread out? So it tells us, right, how do they change and how do they spread themselves out? So we're going to take a look here and we're going to quantify or give a number to how much the data is spread out. So if our data, if when we finish, the mean absolute deviation is a bigger number, that means it's more spread out. It's not very consistent. You can't really count on it. Where if you have a smaller number for your mean absolute deviation, that means your data is more compact. Like you can count on that it's going to be very close to that every single time. Like that's a consistent thing you can count on. So when we find the mean absolute deviation, we're finding the mean of the distances between the data values and the mean. So let's take a look, and I think it will make a lot more sense once you see it in action. So we know our mean was 30 for both of them. Both of them had an average of 30 minutes. Helen spent an average of fair share of 30 minutes. Jeff spent a fair share of 30 minutes each day. So Helen, we want to know her first day she practiced 35 minutes. How far away is that from 30? So take the bigger number, 35 minus 30 is 5. So we'll always take that bigger number to give us a positive distance. An absolute value is always positive. So how far away is 25 from 30? 30 minus 25 is 5. So we can see here, this time she practiced more than her average, so that went in front. The second day she practiced less than the average, so that went behind. So the bigger number always is going to go in front. And then we just subtract, and it tells us how far the distance is from her average. 30 to 30 is 0. So she went a distance of, so she did exactly what she needed to that day. And then 30 minus 20 is 10, and 30 minus 40 is 10. So I want you to take a second and try Jeff's and see if you can figure out. So remember, his mean was 30. How far away were his minutes he practiced away from his fair share average? Let's go ahead and see if you can complete this part. So 45 minus 30 is 15. 55 minus 30 is, I need to fix that there, is 25. 30 minus 5 is also 25. And 30 minus 15 is 15. 30 minus 30 is 0. So now that we know the distances of everything, we're going to find the mean of those distances. So we found their absolute value here in their distances. Then we're going to find the mean and see how far are they spread out away from where they should be, which is 30. So we're going to take our distances and add them up. And lots of times these are going to be some smaller numbers than what we were working with before. So 10 and 10 makes 20, and here's 10 more. Plus a 0 is 30. And when we find the mean, we have to fair share and give it to all of them equally. So she still had 5 days. Even though this was 0, it's still a piece of data. So 30 divided by 5 is 6. So her data was spread out within kind of an average of 6 minutes of the mean. So any day, give or take, she spent anywhere. So 30 minus 6 is 24. So she spent on average anywhere from 24 to 36 minutes, and it averages out to 30. So let's take a look at Jeff's data here and see how much his is spread out. So hers is not spread out too much. All of the numbers are fairly close to the average of 30. Some a little bigger, some a little smaller. Let's see how Jeff's measures up to Helen. So I can see 25 and 25 is 50. 15 and 15 is 30. 50 plus 30 is 80. With a 0 is still 80. And he still practiced 5 days, so we're still dividing by 5. So let's see, 5 goes into 8. 1 time is 5. We've got 3 left over. 6. So we can see his mean absolute deviation is 16. And hers is only 6. So what does this tell us? So I know they both got their piano practicing completed for the week. If they had to do 150 minutes, they did it. I can see that Helen has a smaller mean absolute deviation. She was more consistent at doing the same, close to the same amount every day. Where I can see Jeff's data is much more spread out. So he's got a bigger difference in the amounts that he practiced every day, right? He started off the week really strong and then kind of tapered off throughout the end. Then maybe had to make up for it on the last day, where Helen pretty consistently did the same thing. So smaller absolute deviations are just telling us that data is more packed together. And the bigger ones are telling us that it's more spread out. It's not as consistent. So go ahead and complete task 1 and then come back when you are ready for task 2. Task 2 tells us that Anna and Joe recorded their times during the 50-meter dash. Find the mean absolute deviation for each sprinter's time. So mean absolute deviation. Who is the more consistent sprinter? So here's Joe's times, here's Anna's times. So first we want to find the mean. So we're going to add these up. So remember, we line up our decimals. So here's another 7, 7. Oh, these are going to be nice and easy to add. So you can count in 7. So 2 plus 3 is 5, 7, 14, 21, 28. Oh, I feel like I skipped one. 7, 14, 21, 28, 35. So Joe's total time was 35.5. And we are going to divide that by 5 to see his average time per race. So that goes in there 7 times and 1. So Joe's average is 7.1. So he ran some a little faster, some a little slower, average 7.1. So now let's check out Anna had 7.4, 7.2, 6.9, 7.3, and then a quicker one at 6.7. So here is 10, 19 plus 2 is 21, plus 4 is 25. And then we've got 6 and 12, 7, 14, 21, plus 12 is 33, 34, 35. So altogether, they had the same time. That means their average, she also ran 5 races, is the same. So they're running on average the same. But as a coach, you might have to, if you've only got one spot for a runner, you've got to decide who is going to be more consistent. Like maybe one of them was just having a good day versus a bad, and you just can't really count on them. Like, what are they going to do today? I want to put in the person that I know can give me the best results. So we know their means are both 7.1. So that doesn't help me make a decision. So I'm going to dig deeper to make this decision. So we can see Joe here. So we need to decide 7.3 minus 7.1. So we're finding the distance from the mean to their race time is 0.2, 2/10. So 7.2 to 7.1 is a difference of 1/10. 777, so these ones are pretty easy to get from 7 to 7.1 is a difference of 0.1, 0.1, 0.1. So go ahead and see if you can finish Anna's chart here and then come back and let's check. So she was also a distance of 7, or a mean of 7.1. To get to 7.4 is 0.3. 0.1 to 0.2 is 0.1. So 6.9 up to 7.1 is 0.2. 7.3 down goes 0.2. And 6.7 up to 7.1 is 0.4. So I know their totals now. How far away are they deviating? Now I want to find that average here. So here are the charts here. So we want to find the mean. So we're going to add these up, which is a pretty easy number. 2, 3, 4, 5, 6. So 0.6, and we're still dividing by 5. There's still 5 races. Seeing how the mean of these 5 differences. So this goes in here one time, which is 5, 1 left over, bringing down a 0, 0.6, 0.60, still 6/10, goes in there 2. So his average mean absolute deviation, I always call it average, mean average, those mean the same thing, is 0.12. So that's a very small number that he is deviating. Like he is really close every time. So let's take a look at Anna and see, is she more consistent or less consistent than Joe? So go ahead and add these up. So I can see here that there's 4, 5, 6, 7, 8, 9, 10, 11, 12. So she's got 0.12 here, or actually, I need to carry my 1. This is what happens sometimes when I do math in my head and don't really think about what I'm doing. So this would be the decimal goes straight down. So 1.2, and then we're dividing by 5. So it goes in there into 12. 2 times is 10. 2 left over. I'm going to bring down that 0 placeholder. Goes in there 4. So Anna still has a very small absolute deviation. And this is Joe. Hers is 0.24. Like if I'm talking about many, 24 cents is not going to buy me very many things. That's a really small deviation. Anna's pretty consistent. But as their coach, if I have to choose, I'm saying that Joe is more consistent. His numbers are even closer together. I can count on Joe to produce the results that I need. Like if I need somebody to run this race in 7 seconds, it's looking like Joe is going to consistently do that. Where Anna definitely can, but she also has more that are higher. She's got some that are lower and higher. You just can't always count on her to produce that result. I mean, she's really good. 0.24 is a very small deviation. So let's take a look at what does this tell us. So Anna's data has a greater MAD, right? 0.24 is bigger than 0.12. Or is Joe's bigger? Or they equal? So whose times are more spread out? So remember, the bigger the MAD, the bigger the spread. And if it's smaller, that means who is more consistent? The smaller MAD is more consistent. Or are they equal? So go ahead and complete task 2 and then come back when you are ready for task 3. Task 3 is just reminding us what the mean absolute deviation is. It's just telling us how much the data points are spread out from the average. Bigger spread, less consistent, smaller spread, closer together, more consistent. So Aaron surveyed people in his apartment building to find out how many computers they owned. So we can see that here. So he asked the people living in apartments A through J how many computers they owned. So he added these up and divided by, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And he found that the average was 3. So they've already done part of the work for us. How nice. We love when they do that. And they even went a step further and told us that the mean absolute deviation is 1.4. So we want to see which of these values lie inside this deviation, or which ones are outside of it. So which ones are common, which ones are not common. So we need to find the distance to get from the mean to their computer. So this person had 1 computer. The average is 3. So they have a difference. I've got these circles in the way of my 3. So the difference is 2. This person has 5 computers. The average is 3. So the difference is 2. This person has 3 computers and the average is 3. So there's no difference there. So I want you to see if you can finish listing how many computers or the distance to the mean for each apartment. So 2 to 3 is 1. 7 to 3 is 4. 3 to 3 is 0. 3 to 2 is 1. 1 to 3 is 2. 2 to 3 is 1, and 4 to 3 is 1. So here's the differences. So now let's think about who is falling outside of that deviation. So one way we can do this is to take our mean and we add on the mad. So our mean was 3. The mad was 1.4. So I actually don't need to write those there. So the mean was 3. We want to add on that deviation of 1.4. So 3 up to 1.4 makes 4.4. So anything up to 3.4 or 4.4 is normal. And then we're going to take it away and find that range on the bottom. So this is 3 minus the mean absolute deviation is 1.6. So anything from 1.6 up to 4.4 is within that normal range. So, I want the different chart here. I want this chart to compare computers with, not the distances. So I can see that apartment 1 is not between 1.6 and 4.4. So apartment 1 is outside of the deviation, of the average, of the normal range. And it's pretty common for people to have computers, oftentimes even more than one device within a family. So 5 is also a little outside of the normal, but 3 was the average and fits in there perfect. So this one is within. 2 is within these numbers. 7 is outside. So I'm going to let you finish and decide, are these numbers of computers they have within this range, or is it outside of that range? So go ahead and finish and decide which apartments are within the mean absolute deviation between 1.6 to 4, and which ones are outside of that mean absolute deviation. You can also take a look at this, right? If it's bigger than 1.4 away, I know it's not going to fit in there. This was saying it was 0 away. It fit in between the deviation. This was only 1 away. It fit within that 1.4 distance away. This one was 4 away. This one is 0 away. So there's a couple ways you can look at it. You can either look at the distance, or you can just find this range and see which ones fit in there. Okay, go ahead and complete task 3 and work on your check for understanding for today. And we'll do a few more days of practice for this. So remember, we're finding the average. Make a chart that lists the differences. How do I get from the number to the mean? Number to mean. So we're doing a subtraction problem. Add up your distances, divide by how many there are. That tells you your absolute deviation. Smaller numbers are more consistent, closer together. Bigger numbers, that means it's more spread out, not as consistent of data. Hey, go ahead and finish that up and let me know if you need any help.